Hello and welcome to Investigative Math. This is the fourth video in this series about confidence intervals, and in this video we'll be looking into figuring out confidence intervals for proportions and for the difference in population proportions. So of course, whenever we're creating a confidence interval, right, anytime we're creating a confidence interval we have to use this formula, right? Confidence interval equals our point estimate, and for a proportion that's going to be a symbol we use called p hat, which is our sample proportion, plus or minus our critical value, multiplied by the standard error of our distribution. So let's say that we're trying to find a confidence interval, a 95% confidence interval, for the number of students that are taking statistics. So let's say you sample 100 people, and out of that, 20 are taking statistics. How would we create a confidence interval for this? So first of all, our point estimate, right, our sample proportion is just 20 out of 100, which is 0.2. And then if we want to find the z critical value, we've done this in previous videos. But what you do is you go to statistics, distributions, and then you have to use an inverse normal. And then, of course, for a 95% confidence interval, for a 95% confidence, we use an area of 0.975. I've gone over that in previous videos. If you're not comfortable with that, then go ahead and look at some of those other ones. But I'm not going to go through it again. So we get a critical value of 1.96. And then we have to multiply by our standard error. And the formula for standard error of a proportion is the square root of p times q divided by our sample size, right? So p is our sample proportion, and you can think of it as like your success rate. Q is like your failure rate. So in this case, if 20% are taking statistics, right? If our proportion is 0.2, then our Q is going to be 1 minus that, or 0.8. But sometimes you'll also see this written like this, p hat times 1 minus p hat over n, but this q and this 1 minus p are the same thing. And then we'll divide that by our sample size of 100, and this will give us our 95% confidence interval. So if I take that, multiply by the square root, 0.2 times 0.8 divided by 100, and then we add that to 0.2 for our high end, subtract it from 0.2 for our low end, so it looks like the true proportion of students in the school that are taking statistics is between 12% and 28%, approximately. Okay, so that's pretty straightforward. I'll go ahead and show you how to do it on your calculator as well. If you go to statistics, and then confidence intervals, and then number 5 is for one prop z interval. So all you do is you type in number of successes, the number of people you sampled, and then your confidence level. And click OK, and see it gives us the exact same thing that we calculated before. Right, so you got that 0.278 and 0.12. All right, pretty straightforward. Now we're going to get to a slightly more difficult example, which is finding a confidence interval for the difference in two proportions. So let's say we have school A, and out of a sample of 250 students, 70 of them were taking calculus. And then you have school B, where out of a sample of 500 students, 60 of them were taking calculus. 60 of them were taking calculus. And there are some assumptions that you have to make in these proportion intervals. But just remember that if he's asking a question of this, if he's asking a question like this of you on the math test, I mean, he's not going to ask a question that you just can't, that you plain can't solve. He may ask a question where he's talking about the different conditions, but those are pretty easy to find, and I won't go into a lot of depth here. I might go in more depth on the actual statistical test videos, but not right now. So at school A, we sample 250, 70 of them take calculus, At school B, there's 560 of them take calculus. So we have to find a distribution for the proportion of A minus the proportion of B. That's what we're trying to find, right? So what would be our point estimate, right? What would be our p hat in this case? Well, this one's pretty easy. You just take the point estimate of A and subtract out the point estimate at B. So it'll be 70 divided by 250 minus 60 over 500, right? Proportion at A minus the proportion at B. And you get a difference of 0.16. So that's going to be that. Now, for finding the standard error, it's a little bit trickier. Oh, and by the way, I am finding 95% confidence in this case. For the standard error, we have to use this formula called the Pythagorean theorem of statistics that you may have seen in previous videos. So standard error of A minus B equals the standard error, or the square root, the standard error of A squared plus the standard error of B squared. Okay, so the standard error of A would be, let's see. We have a formula for standard error. We already figured that out, right? Square root of PQ over N. So the standard error squared would just be PQ over N. So this would be the square root of, my pen is not being nice to me. Yeah, so that would be the square root of 70 over 250 times 1 minus 70 over 250 divided by 250, right? PQ over N. Plus, and then for B, it would be 60 over 500 times 1 minus 60 over 500, all divided by 500. So if we go ahead and calculate this, I'm going to do this on my calculator, not on the computer, because I can type faster, and this is a little bit to type in. But you should still be following along on your own calculator. So you should have gotten a standard error of 0.0319. Let me double check that I did my math correctly. Yes. Yes, so you should have gotten a standard error of 0.319. Right? We're doing 95% confidence, and we figured out from before that that means that our critical value is 1.96. So our confidence interval is 0.16 plus or minus our z value, which is 1.96, times our standard error, which is 0.0319. So 1.96 multiplied by 0.0319, right? And then add that to 0.6 for the high end, subtract it from 0.6 for the low end. So it looks like it's anywhere between 0.097 and 0.223. That's the difference between population A and population B, school A and school B. Okay, once again, there is a way to do this on the calculator. I like showing the full formula just because in case he asks something that you can't use the calculator for, you would have to know the formula. Okay, so let's see. It's going to be under statistics and confidence intervals. And then number 6 is for a 2-prop z interval. And this is for finding the difference. So we'll have 70 and 250, right? And then 60 and 500. And of course, 95% confidence. Click OK. And you see we get the same C lower, C upper that we had before. Okay. One last thing that we're going to do, and this is something that he likes to ask pretty often, actually. It's finding the largest sample size for proportion such that you have a certain margin of error. And I realize I might not have actually used the word margin of error during this video series, but you know what it is, right? We've been sort of talking about it without actually talking about it. Right? So this is our formula for confidence interval. The margin of error is basically just this number that we're adding to our point estimate. So this number right here, this critical value times the standard error, this is equal to your margin of error, right? That's just the amount that we've been adding or the amount that we've been subtracting. I may not have actually said those words before, but you know what they are, like you've been working with them already. So a pretty common question that he'll ask is, assume that you have that you want to create a 98% confidence interval, right? And you want the margin of error to be less than 2%. How about? You want the margin of error to be less than 2%. What sample size do you need? How many people would you have to sample in order to get this margin of error to be less than 2%? So we can set this up relatively easy, right? This is the formula for our standard error, right? Z star times our standard error. And we want this to be less than 2%, so less than 0.02. I'll usually just set it equal to 0.02 and then realize that I'll have to round it up because more people would result in a smaller margin of error. Hopefully that just makes intuitive sense. So first thing we have to do is find our critical value. For a 98% confidence, we're going to do an inverse normal and use the 99th percentile, 0.99. So we get a Z star value of 2.326. 2.326. And then our standard error equation is the square root of P times Q over N. So you may think this is a little bit weird, right? We don't have values for P and Q. And we're trying to solve for N, so it's not like we can solve for those. We only have one equation. So here's what you do. Pretty much, you're trying to find the worst case scenario. And so imagine that I was just solving this normally, right? I'm going to solve for N in terms of P and Q, and then this will be a little bit clearer. I'll have the square root of PQ over N equals 0.02 divided by 2.326, right? And then if I square each side, I'll get PQ over N equals this whole thing squared, right? And then if I'm solving for N, which ultimately is what I want, right? I get N equals PQ divided by 0.02 over 2.326 squared. Okay, so this, if we had P and Q, this is how we would solve for N. Well, basically, the way you think about it is you want N in the worst case scenario. It'll say, what is the smallest sample size that would guarantee a margin of error of less than 2%? And you see this value of P and Q, that has an effect on it. So if you want to maximize N, right, you want like the worst case scenario, you want to maximize N, you're always going to plug in 0.5 for P and Q. So if you're trying to find the sample size that'll guarantee you this margin of error or less, then you always plug in P and Q as 0.5. Okay? So let's see. Let's just go back here. It would be 2.326 times, and then 0.5 times 0.5 is 0.25 divided by N equals 0.02. So if we went ahead and solved this, right, 0.02 divided by that, then you square it, and then it should be 0.25 divided by that from the equation that we figured out before. So it looks like the sample size we would need is 3,383 people. Remember, we have to round up because a larger sample would result in a smaller margin of error. So it looks like we would need to sample 3,383 people. Yeah, that's right. 3,383 people. So if you know this thing with the 0.5s, this question is actually pretty straightforward. There is no way to do this on your calculator besides just doing guess and check, which is pretty slow. But this is an example of a question that he could ask, it's a pretty straightforward question if you know how to do it, but if you only know those two confidence interval programs, then you're kind of stuck. So that's about it. Hopefully you learned something. If you did, make sure to leave a like and subscribe. If you think I made a mistake or you think that I should go more in depth on a certain concept in a different video, don't be afraid to leave a comment, and I will see you next time.